Hey, I'm Laken Watson, and I'm going to introduce to you our final product and how our programming department used MathWorks MATLAB and Simulink to program our final product and simulate how well the software integrated with the hardware constructed by our engineering team. Here's a 3D CAD image of our final product, Clementine. Clementine is composed of 2 large motors, 2 small motors, and 3 servos, 2 in the front for our front claw and 1 in the back. Once knowing this, our programming department used the waterfall method to design the software for the robot to be able to move. From the beginning, we created a list of requirements which we detailed in an SRS or software requirement specifications, which are listed here. After requirements, the next phase of the waterfall process is design. This is where we implemented MATLAB and Simulink to design our code, which I will let the lead developer and head programming manager, Adrian, explain.
Hello, my name is Adrian, and as explained, I was the lead developer in the software development process. We've gone through 5 different programs. We began alpha.slx and began configuring the interface as desired by our engineering department. We were told we would have a tank-controlled robot with an arm, 2 front claws, and the back claw. In alpha, we modeled how the tank controls would function as well as how our claws and arms would work. After simulations, we discovered that one of these motors' polarization had to be reversed due to the fact that they are mirroring each other. And as well with our claws here, that way they would open at a full range. So we fixed that in beta. Now in beta, we were told by our engineering department that we would have 2 different arm motors. So we had done that, but we got an issue once we tried to add the arm down. See, in our alpha, the arm only goes down, and in beta, still it only goes down, and we had tried to add the function for it to go up, and we got a compiling error stating that we can't have the same outputs for 2 different inputs. So we had to redesign the logic entirely in Gamma, and the way we did this was using a switch. Once we start simulations here, you can see that once we toggle down button, the arm goes down. We toggle the up button, the arm goes up. Through simulations, we discovered that one of these motors' polarization had to be reversed, again because they are mirroring each other. If they weren't, the gears would burn out the motors. So at this point, we have a fully functioning tank-controlled robot. We have fully functioning claws, but our arm is our issue. So we fixed the polarization issue in Delta. Here you can see that it works. Once we compiled this to our robot, we had discovered that the arm was very jittery, and once we had an item on the scoop of our robot, it would go down because the arm was too heavy. So we had to redesign the logic for the arm. We got it down perfectly in our final. Now you can see that our robot is moving. Here are the motors corresponding to the joysticks, and these different inputs on the joystick drive the robot at different speed, and this is how it would move. This is just a top view of a robot. Now the bottom, the claws, you press the button, they open, and these are our claws. So this claw would rotate that way 60 degrees, and this claw would rotate this way 60 degrees, and we can scoop items up. This is our back claw, very simple. Just press the button and it opens 60 degrees. So our servo here would make this swing this way, and it would pinch what it needed. And then we have our arm. This was a complete hassle to do, and redesigning of the logic. So here we see you press, nothing is pressed right now, and you can see that we have a constant speed going. And we did this to compensate for gravity, as we kept having issues with objects swaying down the scoop. That was essential to the program. Now we press the arm up, and you can tell our arms are moving. Again, this one has been reversed. The polarization has been reversed for them to move in the same direction, because as you can tell, these are mirrored. Now you press the downwards and they move downward. This is the final product that our robot Clementine used. This is our robot Clementine. in its entire. So here we have the front motors, the front claw, our two arm motors, and our back claw would be back here. So I am Adrian Rodriguez, and I just show you how we designed and executed the Simulink.